So here's page 334, Rogowski, page 334, number 56. What do you think? What should I pick to be my inside function, my u? There's two functions sitting there. They both got exponents on them. What do you think the u is going to be? I could pick secant because secant is inside the squared function, but the derivative of secant is not tangent fourth, so that doesn't help me. So what if I pick tangent to be the inside function? Well, the derivative of tangent is secant squared, so that works. So I'm going to pick u equals tangent x, right? I'm not taking that fourth power because I want the inside function. I'm really thinking of that tangent fourth as being tangent x to the fourth power. So the tangent is inside that fourth power. All right, then du equals secant squared x dx. Does this match what I have here? Yeah, it matches exactly. So I don't even have to divide by anything. I can just say that secant squared x dx, that's my du. My tangent to the fourth power is going to be u to the fourth power, right? Because u is taking the role of tangent x. So this is here, and the secant squared is tied up in that du, so it's the secant squared is also in here. And then I have my integral, and then I just do integral of u to the fourth, u fifth over 5 plus c, sub back in, so I have, I'll write it like this, 1/5 tangent fifth x plus c. There you go. That's Rogowski, page 334. Number 56. So I picked the Rogowski because he has sort of a better selection of the indefinite integrals. All these are indefinite integrals because there's no limits. Our result is not a number, it's a function, and it has a plus c in it. Those are all attributes of indefinite integrals. Let's now look at definite integrals with substitution. And those are in our regular textbook, the orange textbook. Finney, DeMana, Waits, and Kennedy. Sorry, Miss Kennedy. All right. I think it's a Miss Kennedy, right? So it's oh no, it's Daniel Kennedy. They're all dudes. Ross Finney, Franklin DeMana, Bert Waits, and Daniel Kennedy. We got Bert, but no Ernie. All right, so we're going to do a definite integral with substitution. So we're going to do in our regular textbook, page 338, number 54. So this is in your textbook, chapter 6. In fact, it is section 6.2. All right, and you have, and by the way, I already wrote it down, and I forgot that I wrote it down, flip the page. All right, there it is. So I've wasted so much time now. So there are two main different ways to do it. I do it a way that makes sense to me, but professors could argue correctly that I'm taking a certain shortcut where I'm writing something a little bit illegitimate. But I'm going to keep writing it that way because it works. But I'll show you what I'm talking about. So first of all, I'm going to show you how I normally do this. So what I would say about this problem is I would say that the inside function is the 1 minus r squared because it's inside the square root. And essentially, we're going to do everything the same way that we do everything else. So and we're just going to evaluate at the end. So I'm just going to find the antiderivative and then evaluate. So I'm going to say u equals 1 minus r squared. So that means that du equals negative 2r dr. All right. I have r dr, but I don't have a negative 2. So I need to divide that negative 2 over. So I'm going to multiply both sides by negative 1/2. And then I'm going to have negative 1/2 du equals r dr. Then that r dr, I'm going to substitute as, I'm going to call it du on the outside, and I'm going to take this negative 1/2 and I'm going to put it out here. So that really that r dr is showing up in two places. The negative 1/2 du is replacing the r dr. All right, and then I have integral 0 to 1 of the square root of something. The square root of what? It's just the square root of u. All right, so now I have, I'll rewrite that because I don't want to do the integral yet. I want to write it as an exponent first, u to the 1/2 du. So notice as soon as I sub in my u's, I have only u's, no r's. R's and u's are not mixing here. All right, now I'm ready to evaluate. So this equals negative 1/2 the evaluation of, so we're going to raise the exponent 1 and divide by the new exponent. And here's where I'm going to do something that some professors don't like. However, it works. I'm going to keep these limits here 0 to 1. All right. Now, a lot of professors will say, you can't do that because the limits are values of r, not u. So what is implied here, but I usually don't write, is this is r equals 0 to r equals 1. But the variable in here is u, so they're different. But see, it doesn't matter because I'm going to sub it back anyway. But first I'm going to pull out this 2/3, so the 2 is going to cancel with that 2. I'm going to have negative 1/3. Generally, if you have a constant, pull it out before you do anything else. It'll just make it easier. Now, see, I'm just putting 0 to 1 here, but I mean r equals 0 to r equals 1. Again, some professors don't like that. Some teachers don't like that, and it's technically wrong. All right, so just so you know, but I'm always going to write that anyway, so too bad. I'm a rebel. Deal with it. So then my u is going to be 1 minus r squared. So now, see, I'm going to sub back in the r. And this is actually what I like about the method that I do it, is that when you do this, you got to substitute back the r. Now, as soon as I do that, now technically here I have to say r equals 0 and r equals 1, but I usually don't. Once I've gotten here, I put the r back, so now the variables out here match the variables in here again. All right. Now, I'm not really going to talk about this a lot in my subsequent examples, but you should just know that that's sort of a shortcut, and I'll show you how other people do it, and you can decide how you want to do it. All right. So now I just plug in my values like always. I don't think there's anything else I can do here to substitute, so we'll put negative 1/3. We're going to put in the 1 first, so we're going to have 0, and then we're going to put in the 0, and we're going to get 1. All right. So then we get a positive 1/3 for our value. All right. Easy peasy, right? Okay, now here's how many professors really like you to write this. They actually would say that, Reese, you actually got it wrong here, even way up here. Okay, because as soon as you change the r to a u, then these values don't match these values, because these out here are r equals 1 and r equals 0, but this is u. So what many teachers and professors and mathematicians like to do is they like to say, okay, let's actually write this integral with the correct limits. And so what they'll do is they'll say, okay, our substitution is u equals 1 minus r squared. So what is u of 1? All right, u of 1 is equal to 1 minus 1 squared, which is 0. All right, and u of my lower limit, u of 0, is equal to 1 minus 0 squared, 1 minus 0 squared, which is 1. So they would say what you really should write for this integral is the integral from the integral of negative 1/2 from 1 to 0 of square root u du. All right, then do all the same stuff, but then when you get to here where you have negative 1/3 u to the 3/2, now our limits now, instead of being 0 to 1, they're 1 to 0. I don't like the larger numbers on the bottom. Now, the advantage of this is you don't have to sub the r back in. Right over here, I subbed the r back in, but people who do it this way are going to say, look, you changed the values of the limits to match the correct variable. These are values of u now, not r. Therefore, I can just plug them into this expression without changing it back to r. And then I get, when I plug in, I'm going to plug in the 0 first this time, and then I'm going to plug in the 1, and I still get 1/3. All right? So I think you can make a pretty strong argument that this is more correct, unless you sit here and put r equals on every single one of these, which no one ever does. But you're normally going to see me do this way. One of the things I like about this way is that, when we do an indefinite integral, there's always the step at the end where you have to sub the u back. We do a definite integral. If you do it this way, you don't have to sub the u back. So like you have a different process for different definite, indefinite integrals. So some people will make the mistake of subbing the u back, even though they already changed the variables. So I like that it's the same steps, but yeah, there is this variable conflict as you go. So as we go along, I'm always going to do it this way. Sometimes some people might bug you to do it this way. And there you go. That is a little bit about doing definite integrals. We'll do a couple more examples coming up.